Can you see the blackboard? Somebody reply.
Yes, sir.
Yes,
Okay,
sir.
great, great. Now let's begin. And we had started talking about two kinds of things. One was something called embedding. And the other was something like quotient map. So what I thought is, let us look at this in the category of sets. Let us look at this in the category of sets. Meaning now I want X and Y to be sets and F simply to be a map of sets. Let's forget all topology, groups, metric spaces, rings. Just keep sets and set maps. So in that context, let us look at embedding and quotient map. So here we go. So in sets, there is something called injection. F X to Y, injective. Let be an injective map. Be an injective map. Okay. Once it is an injective map, it has the following great property. So if X to Y, F is injective, and Z is any other set, and this is any other map, this is injective. This is any other map with the property that image of G is contained in image of F. Suppose that, okay, now comes the universal property and that will be in red. Then there exists a unique map H from Z to X such that G is equal to F composite H, which means there exists a unique such map H, making this triangle commute. Everybody happy with this universal property of injective maps? Yeah, clear?
Yes.
Is it clear? Can you hear me?
Yes, sir. Yes, sir.
Yes, and is the property also clear? Because you see, what is happening is, if I take some element, let's call that element small z here. Small z belongs to z. That goes to something called gz. But that's in the image of G, and you are told that image of G is image of F. So this gz has to be equal to some f of x. And for a unique x, if x exists, if such a x exists, such an x exists, it is unique as F is injective. So there are no two different elements here which are mapping to the same element here. So if at all this image is contained in the image of F, then there's a unique small x such that this is true. And once that happens, now you know how to define. Now you send this Z under this red map. So let's print the map red. Under this red map, you are forced to send it to X, because X is the only thing which maps to Fx. So you see, there exists such a unique H. Is the proof clear? This is the universal property of injective maps. This is what makes injections so great. All the time you have read injective map, injective map. So this summarizes why injective maps are so useful in sets. They have this property. Now let us look at that same problem in topological spaces. Now let's go to the category of topological spaces. Now arrows are going to be continuous maps. So I have a continuous map F, Y. Suppose this is continuous and injective. And suppose I have some other topological space Z, and this is a continuous map. And moreover, G of Z is contained in f of x. Image of G is contained in image of x. Question. Does there exist a map H Z to X, continuous map? Now all maps are supposed to be continuous, such that this triangle commutes. Does there exist some H such that this commutes? Okay. So G equal to FH, and next is H unique. These are the two questions we have to ask. We want to know, do topological spaces and continuous maps behave like sets and set maps? Just the category is different. And anybody wants to answer, is there going to be a map H as sets first of all? Forget topology. Will there be a map H? I don't know whether H is continuous. Will there be a map H? Chalo, answer. Somebody willing to answer whether there is a map H? Have I lost connection, or are you guys on a strike? Can anybody hear me?
Yes, sir.
Now, does there exist a map H as sets? Because this is the same diagram as here, so there does exist a map H. It has to be defined by this same formula. Because where can you send a small z? Well, its image is the image of a unique point from here, because this is injective. So I have to send it there. So there is a unique map H, except I don't know whether it's continuous. Is that clear that there is such a set map?
Yes. Yes, sir.
Yeah. Now, will H be continuous? So the answer, let us write what we found already. We found that answer is, as a set map means not necessarily continuous. H exists and is unique. But is it continuous? And the answer you will see is no. I'll give you an example, meaning not necessarily. So here's an example. I take my topology X to be R with discrete metric, discrete topology. Let's take Y equal to R with usual topology. And let's take f x to y as identity of R to R. And let's take again Z to be R with usual topology. So what is happening is Y looks like this, all these points nicely arranged. X looks like all points all separate. It's like somebody has taken a big hammer and broken R into tiny pieces, broken it into sand. This is how X looks. This is how Y looks. One of these points is root 2, one of these points is -1, one of these points is pi, one of these points is e, one of these points is 22 by 7, which is a number very important in primary school, and so on. All these numbers are now pretty separate. This is that same set with discrete topology. All have a little open neighborhood. And now this map is continuous, of course. But now this identity map from here to here does not factor through a continuous map to this. See? समझ गया? So just being a continuous injection does not give you this universal property. So to have the universal property, f x to y should be an embedding. That is a subset u in x is open if and only if there exists an open subset V in Y such that U, U and wrote me, is that F inverse V is equal to U. This is the property. Once this is there, the factorization will be continuous. Why? I want to show the inverse image of an open set here is open. But what's an open set here? It's the inverse image of some open set here. So I want to show that the inverse image of this open set and of that inverse image is open. But since this is a set theoretic factoring, that inverse image is directly the inverse image under this map. But this map is continuous, therefore that inverse image is open. So that shows that the inverse image of all those sets is open here. So this map is continuous. Okay. So we have shown that this nice property in sets is achieved just by being injective. To have the corresponding property in topical spaces, the topology on X should be such that every open set here should be the inverse image of an open set here. It's not enough to say that inverse image of an open set here is an open set here. No, other way also. Given an open set here, there should be an open set here whose inverse image that is. And then it is an embedding. So what's the simplest example of embedding? Simplest example, let X, this is a topical space, this is a subset, and let I from X to Y, the inclusion map. Now we have to make X a topical space. So give X the subspace topology. Then X becomes a topological space, which is a subspace of X, not just a subset now. Earlier it was only subset. it becomes a space, and I from X into Y becomes an embedding. If I want to make I an embedding, this is the only topology I can give it, because I want all those sets here to be open, which are inverse image, meaning intersection of X with some open subset of Y. That was the definition of subspace topology. Subspace topology is what makes the inclusion map embedding. But there are all kinds of nice examples in everyday life of embeddings.
May I ask something, please?
Yes.
Yes. You just said that this is the simplest example. Hello?
Yeah.
Could you tell me in what sense you mean simplest example?
No. And I won't define example, and I won't define simplest, and I won't define sense. So the non-mathematical words are English, and they have their English or psychological meaning.
Okay.
All right. Now, now let's. So some of these are psychological words designed for education. Simple means what? In my opinion, where I may be mistaken, you guys will find it easy to understand. Again, do I define what is meant by easy? No, I'm not giving a course on psychology. Okay, all right. Now, let's give examples of embedding. So I have R2. Here's R2. And I have circle S1. On the other hand, I have all kinds of things called simple closed curves. And all these are embeddings. Okay, I leave it to you to make the example precise, because I am not going to define a cat, and I am not going to define a simple closed curve. You see, all these simple closed curves are embeddings of S1 in that. So all the time you will encounter embeddings. Okay. Now, now, who was the guy who wanted to know simplest example? Was that Ishan?
Yes, but I had a reason, because
No, but for your entertainment, I'll tell you more.
Thank you.
Okay. So for your entertainment, I'll say that we defined all this in terms of points and images, right? So it's not entirely nicely categorical the way it can be made.
Yes, and that's why I said that I think every embedding is actually a subspace.
You know, the notion of subspace is difficult to define. Anyway, all right. So what I was going to tell you, Ishan, is perhaps you know words like strict monomorphism. Do you?
No, sir. I don't know what is strict monomorphism.
Okay, all right. Doesn't matter. Okay. No, in that case, you talk with me later, and I'll tell you some very interesting examples.
Yes, sir.
I'll change the category to that of rings, for example, and I'll show you what funny things can happen in rings. Okay. Now I'm going to, so here we are, since we are talking of categories, let me revert to the previous stuff and give you one example. Example of categorical argument. The reason I give this example is it came up in my last set of exercises. You have to argue categorically as much as possible, right? So here's an example of categorical argument. Suppose I have x to y, f, this is a continuous map. And suppose I have Z to W, G, another continuous map. Then to solve my last set of exercises, you need to show that X cross Z to Y cross W, this map which I'll call F cross G, show this is continuous. This is continuous. And what is this map? In set theoretic terms, easy to define. This is the map which sends small x comma small z to what pair? Somebody tell.
It sends it to fx comma gz, but we can construct it categorically and immediately one can say
that is the example. That is what I want you to do. So how do you construct it categorically? I orally explained it in my last lecture when I wanted to say that x comma y goes to x square plus y square is a continuous map, and etc., etc., etc. So in all such things, we were using such things. So what happens is x cross z has first of all a map to x. What's this great map? Projection on x. It also has a map to z. That's called projection on z. Now there's a composite map going to y. This is f. And here's a map going to w. So x cross z has one map, and now I'll write that composite map in a different color. So x cross z comes with a pink map to to y, and a pink map to w. Therefore, by the universal property of product, it should have map to y cross w, and y cross w has this first projection q1, this second projection q2, and there should exist a unique map here H, making this and this commute. And this H is exactly this map F cross G. This is how you construct F cross G. Now, I'm telling you this because of the following. You do not need to. Should not is another matter. People do all kinds of things which they don't need to do. But you do not need to recall what is the topology on y cross w and laboriously show that inverse image of each open set y cross w is open in X cross Z. You don't have to do this, okay? Because the proof is here simply by arrows. Advantage of a proof by arrows is, if I now give you a second exercise, let X, Y, Z, W be groups, and F, X to Y, and G, Z to W be group homomorphisms. Then show that F cross G, X cross Z to Y cross W is a group homomorphism. Now you may think that this exercise looks like this exercise. To do this, I'll recall what's the basis, what's sub basis, whatever, show inverse image of each of them is open, and then their intersection. Arbitrary unions, finite intersection, you keep it. Here you will try to recall the group structure on this and then show that if I take two elements here and their product goes to product in this group under this map, so it's a group homomorphism. No need to do any of it because this is already a proof in all categories. any category. So this is a proof. So this works in any category which has binary products. So a whole lot of categories that you know, all of them have binary products. Metric spaces with non-expanding maps. So then this map H is automatically a non-expanding map. You don't have to again write the metric and check inequalities. This proof is master proof for everything. Okay, it's like your silo theory theorems, right? If a group has some order divisible by prime, then some element of that prime order, whatever. It doesn't matter whether it's a group of matrices of size 17 by 17. You don't have to write your elements as 17 by 17 matrices and remember the definition of matrix multiplication in order to say that that group is going to have an element of order P, right? Because the group property is enough. So here the categorical property is enough. Just as matrices and whatnot are concrete examples of groups, the entire category of groups is a concrete example of a category. And so completely general categorical example will apply there, provided the needed construction, namely binary products, exists there. Is this point clear? Silence. Okay. All right. Now let's go to the other kind of maps, which are quotients. So I have said enough about sub. Now I'm talking about quotient. Quotient morphisms. So first, let us do in sets. In sets, these are surjections. Okay. So what is the universal property? Let's look at the property. So X is a set and Z is another set, and this is F and this is a surjection. Surjection is some fancy word for onto, as they were called perhaps in your school. But I think you're all familiar with such words. I don't know. I had no contact with MSc students for very long time, so I don't know what is your standard vocabulary. Do they use words like surjection in your college? Or do they say onto?
Both really.
No, surjection is fine, no? Surjection onto, you're familiar with all these words. Great. Okay. So now this has the following universal property. Universal property. Now at this point, I would dearly love to write things like X, Z. This picture, unfortunately, I cannot yet draw because I have not yet introduced this very important object, which I will, which I have mind to introduce. Okay, all right. So instead, let me put it in some other way, using elements, making it slightly less categorical, general. So suppose I have any other map to W, and suppose G has the property, that if two elements, if Gx1 equal to Gx2, then Fx1 equal to Fx2. Okay. G has a property that if G of x1 is equal to G of x2, then F of x1 is equal. Then there exists a unique map, and I'm going to show it in red. There exists a unique map H which makes this commute. Such that G equal to H composite F. Do you all agree with this property of surjective maps? So I want to know how to define H. I want to define H. So okay, I take some element. Somebody has some nice music playing with drums, metal sound, but please put it on mute. Huh? Okay. So I want to know where to send it. Where should I send it? Now this Z has to come from some X. Let's say that it comes from X. Because this is surjective. This Z comes from X. So now this X has to go to somewhere called, so this Z has to be equal to Fx. So now send this Z to Gx. Now the question arises, if there was another fellow, so let's call it x1, x1, Z is the image of x1. It may be that there is another element x2, that also goes there. So that's also equal to fx2. So I wrote it the other way around. Very clear in trying to prove it that I interchanged the order which I should correct. Okay, let's correct it. Okay. Yeah. So you see, so both these x1 and x2 have the same image, and my condition is G has a property that if 2 points go to the same point here, then they better go to the same point there. Okay. And because of this property, fx1 and fx2 go to the same point because x1 and x2 must go to the same point gx, which is gx1 equal to gx2. Okay. So I have shown the universal property holds for a surjective map. Any questions at this point? Are you guys with me so far? Because I'm going to change my category now. Yeah. Who was asking something? Anybody asking? Okay. So let's now shift to the category of groups. Different category, different color. Let's work in groups. And perhaps you don't like your groups to be called X, Y, Z, etc., etc. So let us give you some nice friendly name for your group. This is a group. This is a homomorphism. And it is surjective. And it goes to some group H. Now this is another homomorphism G, and it's going to K. And G has the property that fx1 equal to fx2 implies gx1 equal to gx2. Assume. Suppose that, but in the case of groups, you are used to writing such properties in a much more compact manner. You are used to saying that if f of x equal to E, then g of x equal to E. You see how these two properties are the same? Because you applied to x1 times x2 inverse. F and G are group homomorphisms. Is it clear? And therefore, this I can further write by saying that this is equivalent to saying that kernel of F is contained in kernel of G. And because this is surjective, this is equal to this isomorphic to G mod this kernel. And now there exists such a unique map making this commute is what you call whatever dot fundamental theorem, first, second, third, I don't know these names. Theorem of group theory, of group homomorphisms. Is it clear to you that a surjective homomorphism has exactly this universal property in groups? Clear?
Yes, sir.
Yes.
So
Great.
can you please repeat this?
Yes, yes. So look at surjection in groups. G to H is a surjection in groups. It's a homomorphism which is a surjection. I am claiming that it has exactly that property. Namely, if there is any other group homomorphism to any other group, such that kernel of this map is contained in kernel of this map, meaning kernel of this map goes to identity under this, which also means if two elements go to the same element here, then they go to this element here. You see, this is equivalent to saying that f of x1, x2 inverse equal to E, right? This is the same as this. And this is the same as saying that x1, x2 inverse belongs to kernel of f. And this is amounts to saying that x1, x2 inverse belongs to kernel of G. Which means if an element belongs to kernel of f, then it should belong to kernel of G. This is that condition, kernel of f contain kernel. If that happens, then there exists a unique group homomorphism H going from here to there, making this triangle commute. And this is called the fundamental theorem of group homomorphism. I'm not sure about the last thing because such nomenclature I am not familiar with. It is some favorite of undergraduates. Yeah, what is it called? You guys have been undergraduates recently. Is it called fundamental theorem of group homomorphism?
So first theorem of isomorphism.
I see. Okay, it is called first theorem of isomorphism. But where's an isomorphism here? There's no isomorphism involved. Or you mean this isomorphism of H with
So
this
H is
quotient?
isomorphic to
To the
G
quotient.
quotient. Yes.
I see. So now you understand this property of universal property of quotient. See, H is a quotient of G. H is the quotient of G by kernel F. It's the quotient group. So surjective map in sets exactly behaves like a quotient map in groups. Understood? Now let us go to topological spaces. Now my question. So first I'll ask what is the universal property of quotient? Property of quotient in topological spaces. So I have X, I have F, I have Y. It's a continuous map. Continuous. Everything is continuous. And it's a surjection. Now I want to know whether this holds. And this is G.
Are you saying that Y is a quotient topology? Are you just saying that you have this setup, or are you putting something else on Y as well?
No. My question is, do you think it is already, this property is already valid, and you are giving me the answer, right? So what's the answer? This property is not already valid. What will make it valid?
If you put a quotient topology on Y, or if you say that Y is defined with keeping that this universal property holds.
That will force the quotient property because
Yes.
this is a unique.
Yes.
So the map H Y to Z need not be continuous. Okay. But to ensure that, yeah. Hello, your voice is getting broken. Can you repeat what you're saying? To ensure that H is continuous, what do you need? See, if there is some open subset W here, suppose this is open, then I want to know whether H inverse W is H inverse W open in Y. And what is F inverse of H inverse of W? Equal to G inverse W. This is open in X as G is continuous. So now I have the nice situation that if I look at this open set, this is an open, sorry, if I look at this set, I don't know whether it's open. I want it to be open. Its inverse image is open. So I should define my topology on Y so that open sets in Y are exactly all subsets A of Y such that F inverse of A is open in X. And so if I do that, then this set, its inverse image under F is, because it is G inverse W, which is open because G is continuous, then this is an open set. So the inverse image of W here is open, and so this is continuous. Set theoretically, it's already a quotient because I have given you it's a surjection. Surjections are quotient set theoretically. So as far as the set map is concerned, there exists a unique H. The only problem was whether this unique map is continuous or not. And to have it continuous, exactly we need the quotient topology. You see how the definition of quotient topology was born out of this requirement of making H continuous, right? So have you understood where the quotient topology comes from? Quotient topology is so defined that the universal property holds. Now somebody may ask, are there two different ways of defining quotient topology? You told us one way. Perhaps universal property can be satisfied in another way. But then to Y and with first topology, and you give some second topology, this is F and this is also F as far as map is concerned, okay? But both are continuous. Both have the universal property, suppose. Then there exists a unique map like this, and that map has to be identity. And there exists a unique map like this, that is identity. So identity from here to here is continuous, and its inverse identity from here to here is continuous. So identity is a homeomorphism, which makes T1 equal to T2. Because if I any open set here, its inverse image here is in T2. So everything in T1 is in T2, everything in T2 is in T1, and so T1 equal to T2. So there are no two ways of doing it. There is only the quotient topology is the only way of bringing about this universal property. So is that clear? So what is in topological spaces? You need a particular spatial topology here for this map to be a quotient map. Being continuous is not enough. In groups, the analog of continuous is a homomorphism, and a surjective homomorphism already has the quotient universal property. And in sets, any surjection has the quotient universal property. So now every time you encounter some category, you can ask, do you have analogs of embeddings and quotients in your category? To make this thing wholly categorical, as I keep telling you, I will like to junk the notion of elements, images, and whatnot, and have notions such as strict epimorphism, this kind of diagram, strict monomorphism, etc., which those of you who want to pursue it are welcome to send me an email message. Okay, now now I am going to come to construction of quotients. Okay. So you see, let's again work with sets. So I have surjection x to y. F surjection. Okay. I am saying that F induces, F defines an equivalence relation on X. How? Fx1 equal to Fx2 if so. This is the meaning of, let's write it the other way around. First, the thing that I am defining should come first. X1 is equivalent to X2 is equivalent to Fx1 equal to Fx2. Is this an equivalence relation? Let's check the three properties. X is equivalent to X. Yes. Second property, X1 equivalent to X2 implies X2 equivalent to X1. Yes. What was the third property? X1 equivalent to X2, X2 equivalent to X3 imply X1 equivalent to X3. Yes. So we have checked all three. I like this fantastic method of checking. You write the property, then you make a tick mark on it, and then you say, we have checked it. You like this? You like this new method of checking?
Yes,
then
sir.
we will always follow it. We will write whatever you want to check, and then we'll write a check mark in front of it, and that's checking. Great. Now, so this is an equivalence relation. And now, so I can go from y, from x to the set of all equivalence classes. And now this will be in a natural bijection with y. Yeah. Because any element of y is the same as the equivalence class, the set of all x, such that f of x equal to y. This is an equivalence class. This is an equivalence class. Okay. Right? So you understood how to construct quotients as going modulo an equivalence relation. You make the set of all equivalence classes. And that's what is a surjection. A surjection involves identifying things together, and everything down there, because it is surjection, comes by identifying something to something to something, perhaps only something to itself. If it's not a surjection, then there may be some surplus elements of y which don't come this way. Okay, now somebody last time was asking me for the word saturated, wanted to see that word used. So let us use that word saturated. A subset of X, and X has an equivalence relation, is called saturated. So let's call that subset B. A subset B is called saturated if B is closed under, okay, and I'll also like to say that B is non-empty here. Okay, B is non-empty and closed. Okay, doesn't matter. Depends on in what context you want to use it. So saturated closed sets are unions of orbits. Saturated sets are unions of equivalence classes. Where should I write it? A set is saturated is equivalent to It is a union of equivalence classes. Okay. So suppose I am in a group. G is a group and H is a subgroup. And the equivalence relation is G1 is equivalent to G2 if G1 times H equal to G2 for some H belonging to H. Okay. Then the equivalence classes are the cosets. All right. So here we are. So how do you make a quotient? To make a quotient, you put all the equivalence classes into a single point. So you now try to define a group structure on the set of all cosets. Will you succeed? It depends. For that, H has to be a normal subgroup. Otherwise, the quotient construction does not work in groups. So in groups, though every surjective homomorphism is a quotient, to make a quotient, you have this extra requirement of normality. In sets, every surjection is a quotient. In topological spaces, not every surjection is a quotient. Moreover, the topology should be such that blah, blah, blah. Okay. So these categories differ from each other. If those categories had exactly all the same properties, then you won't have so many different subjects. Okay, now. So I want to make a construction of quotient. So now let's go to topical spaces. Okay. So suppose I have X is a topical space. And this is an equivalence relation on X. We want to construct a topology on the set such that the map, the canonical map from X to X mod this equivalence relation which sends any small x to its equivalence class. Are you familiar with this notation? I'll use this notation. By this I mean the equivalence class of X. Okay. So that a canonical map, this is a surjection. Let's give it the name Q. Such that the canonical map is a quotient map. And now we have learned how to do it. How to do it? So how to define the topology? So define any subset, let's call it V, contained in to be open in if and only if Q inverse V is open in X. I want to draw a picture, by the way. So in true Grothendieck style, let us write X like this. Let us write Y like this. And the surjection goes like this. So then the fiber over this red point is this. This is the fiber. Fiber over this yellow point. There's the yellow. Fiber over this yellow point is this. So the equivalence classes are fibers. are exactly the fibers. Because this entire fiber becomes a single point here. 2 points go to the same point here is the definition of the equivalence relation. So the equivalence classes are the fibers. Okay. And saturated subset means this is the same as union of fibers. So if I set here like this, just this much is not saturated because there's a fiber going through it, but the whole fiber is not in this subset. So if a fiber intersects that subset, then the whole fiber should lie in that subset. That's called saturated. Okay. And so how do we give a topology? We say that the open sets in Y are exactly the images of saturated open sets in X. So this is a saturated open set. Another way of saying it is if and only if Q inverse V is a saturated open set. Because saturated it already is and we are asking it to be open. Okay. So V is open is equivalent to Q inverse is a saturated open set. So is it clear? This is going to define by the, because we said already what makes a map in topology a quotient map. So we have to define the topology such that the open sets in Y are exactly all the subsets whose inverse image is open. So this is what we are doing here. So given any equivalence relation, we can produce a quotient topology. And so that has the universal property. Let's write it in a different form. X mod theta, and this is the quotient map. Now suppose I have any other map Z. This is some map G. G has the property that x1 is equivalent to x2 implies gx1 equal to gx2. Suppose this is true. If then of course all these are now continuous. Okay, topical space, this quotient topology, this is surjective, which sends x to the equivalence class of X. This is continuous. And there exists H, which is continuous. So that this convex. So then there exists a unique H from X to Z. And how is it defined? Well, take any representative. Any element here looks like an equivalence class. So define H of X to be equal to G of X. This is well defined. Well defined and continuous. It is continuous because it has been given the quotient topology. Okay. So we have told you how to make quotients in topical spaces. You see, when you were in BSc, it was a big job defining quotients in groups, to put the equivalence class together and to define, to make the set of all equivalence classes, and then to define a group structure, to define a multiplication. To see it is well defined. This is the well defined point. And all that required that H to be a normal subgroup. So it was a big thing. I remember even for myself from very long ago that learning the property of quotients of topical groups, quotients of groups, abstract groups by normal subgroups was a very important point in one's education. So now we are doing that same thing in topology. We have defined the quotient topology so that given any topical space and an equivalence relation on the set of all equivalence classes, we have topology with that same universal property. You see, we are achieving the same objective in terms of maps, arrows, commutative triangles, etc., etc. Because finally, we are building a machine which is very uniform across categories. And we are looking for all those nice properties, which then we keep on using the properties. We don't go back to the definition of quotient topology, go back to the definition of cosets and whatnot. All those details go under the bonnet of your car, and you are presented with a steering wheel, and in front of your foot is an accelerator or a brake, and you don't have to anymore bother about how those things are joined to the mechanism and whatnot. The car will work. Turn the wheel this way, it will turn that way, and so on, so on. Okay. So I'll end now, and now there is time for questions if you are